everyone, in this video we are going to see the continuity equation for semiconductors. So this continuity equation is a very fundamental concept. So you can find this equation in various fields such as fluid mechanics, thermodynamics, electromagnetic theory, even in semiconductors. So the concept of this continuity is conservation of certain quantities. Okay, for example, in electromagnetic theory, energy is conserved. Similarly, for semiconductors, charge is conserved. And here we will see the single variable continuity equation in this video. So for that, we will consider a semiconductor material. So here the blue color box is the semiconductor material that is considered, and here the length is x and the cross sectional area is a. And in this semiconductor material we will take a very small box having thickness delta x that is represented here. So this small box will be a into delta x, and suppose n is the electron concentration, that means number of electrons per unit volume, or we can say number of electrons per centimeter cube. Okay, so now suppose the number of electrons in this small volume is increasing, so increasing with respect to time. So suppose the increase is represented by del n by del t, and as we are interested in number, and what does n represent? It is the number of electrons per volume. So we will multiply volume because we are interested in finding out the number. So here I have multiplied the volume of this small box. This is your number of increase in electrons in the box with respect to time. Now suppose Jnx is the current density that is entering into this small box, and Jnx plus delta x is the current density that is moving out from this box. So when as we have assumed that the number of electron in this small box is increasing, so when it will increase? So it will increase when the outflow current is less than the inflow current. That means Jn x plus delta x is less than Jn x, or the opposite is also true. That means Jn x is greater than Jn plus delta x. Now let us write down the mathematical equation for the increase in electrons inside this box with respect to time. So it will be del n by delta t a plus delta x, that is your increase in number of electrons, will be Jnx is your current density that is entering, which is of course more than the current density that is leaving this box. So the total number of electrons will be, then the increase we have to subtract it. So here the first term, it represents the number of electrons flowing into the box. And the second term represents the number of electrons flowing out of the box. And according to our assumption that the number of electrons are increasing, so your current density that is leaving, or the current that is leaving, is less than the current density or the current that is entering into the small box. So this is the condition when the number of electrons will increase. Now, uh, will there be any other reason for increase in the number of electrons apart from the current density? Then the answer will be yes. So again, so the number of electrons in the box will increase when the rate of generation of electrons will be more than the rate of recombination, because we know that there will be generation and recombination of electrons inside a semiconductor, and this generation rate is the number of electrons generated per unit volume. So if you are interested in finding the number, then we have to multiply the volume. So now this equation can be rewritten as, so here we will add two parameters, that is Gn and Rn, to this equation, and the continuity equation will be Jn x into A by minus Q minus then we will add the rate of generation, and as I have mentioned, this rate of generation, the unit of rate of generation is number of electrons generated per unit volume. So here we will multiply the volume as we are interested in the number, and accordingly recombination, the electrons those were lost due to recombination will be Rn into A into delta x. Now if you see this equation, this A into delta x, we can remove this A into delta, will be del n by delta t. That means the increase in number of electrons per unit time, it will be equals to Jn x into minus q by del x. Similarly, Jn x plus del x and plus Gn minus Rn. Now, if I take this 1 by q term outside, so what will happen will be Jn x plus del x minus Jn x divided by del x plus Gn minus Rn. So this will be your del n by delta t. Now, as we are interested in like we are finding out the increase in number of electrons with respect to time, then for this current density term, we can we can add one other parameter, time. That means we will consider the current density at a particular time. Okay, so we can rewrite this equation as del n by del t 1 by q Jn x plus del x comma t. It means we are considering the current density at x plus del x at time t, minus Jn x comma t divided by del x plus Gn minus Rn. Now if you see this term, so this is the definition of partial differential equation. So here del x tends to 0 because we have considered a very small volume in that semiconductor material. So when del x will tend to 0, then this part will be will satisfy the definition of partial differential equation. Now we can rewrite this equation as del n by del t, that is equals to 1 by q into the partial derivative of this current density with respect to distance plus Gn minus Rn. Okay, so this is the continuity equation. So suppose this is equation number 2. Now we know that current density of electrons is due to or we can say it is the addition of current density due to diffusion and due to drift. So suppose this is the drift current density and this is the diffusion current density. So it will be equals to qn mu n into E plus q into dn into del n by del x. So this value, so let us write it as equation 3. Now we will put the value of Jn from equation 3 in equation 2. So if I'll put this value, so I can rewrite the equation 2 as del n by delta t is equals to, let's put the value and rewrite the equation. So it will be n into mu n del E by del x plus mu n E into del n by del x plus del n del square n by del x square plus gn minus rn. So this is your complete equation of continuity in case of semiconductors when we are considering electrons. So for electrons, this is your continuity equation for electrons. Similarly, we can write down the continuity equation for holes, but so if you follow the similar process that I have explained for electrons, so if you try to derive the continuity equation for holes, so the expression will look like this. So the number of increase in holes per unit time will be equals to so this one is the continuity equation for holes. So we have discussed the continuity equation in this video. So if you have any doubt, you can ask it in the comment section. Thank you for watching the video.